Hello. In this video we're going to discuss what science is. If we have survived this long, it is because we have tried to make sense of the world that is ours and that we perceive through our senses. In other words, the sense-perceptible world. From time immemorial, the heavens have aroused the curiosity of man and have made him question. But we should not forget the important role played by the world he lives in. From the very beginning, our distant ancestors were adept at making tools. But what differentiates man from other animals are his brain and his hands. And his hands are connected to his brain through a very subtle network of nerves. And therefore, man has never been content to just build simple rudimentary tools. He has always had a need to make them more perfect. To do this, he has had from early on understand the properties of materials. What you can do with them, how you can displace them, or how you can change their structure, notably through the use of fire. Fire was gradually harnessed as a technique to make not only tools but also artwork. To do this, we had to understand its properties. This understanding, and therefore the study of the sense-perceptible world, can by definition only be achieved through reason-based observation, or rather observation-based reasoning. Conclusions merely guessed at intuitively from observation might be mere coincidence, and they keep us tied down to the particular observations made. This does not allow us to make sense of the world. For example, it might be that we have only observed white swans, but we cannot deduce from that all swans are white. In particular, observation in itself does not lead to explanations. For that, we need to interpret the observation and deduce consequences from it. Observing animals as such, for example, explains nothing, but classifying them into those that fly, those that crawl, so on and so forth, is a very first step towards understanding why we always fall back to Earth. And ultimately, it led us to the idea of gravitation and to predicting the movements of stars. Conversely, reasoning without solid empirical foundations can lead to fanciful theories. For example, Aristotle argued that a stone thrown from the mast of a boat would fall at a distance and not perpendicularly, and had inferred from this that the Earth was stationary because otherwise flying objects would always fall outside the Earth, which is obviously utter nonsense. It is in the 16th century that Giordano Bruno carried out the actual experiment and found out how the trajectories of stones thrown from the mast and from the shore would be perceived by observers on the shore and on the boat. Science ensures that conclusions are minimally reliable, For this, they have to be communicable and therefore verifiable by everyone. This means that observations have to be reproducible at will. Theories that can only be based on limited observation are likely to be what Neil Postman has characterized as unique interpretations with examples in various forms, even though the research conducted may have been systematically done. This is, for example, the case with sociology, which obviously is no comment on its importance. Communicability means that absolute concepts such as heat or height, although they are certainly part of our experience of life, have no place in science, for there is no way of determining how two individuals perceive them. The same applies to concepts such as God, life, nature, and the essence of things. What can be communicated and agreed upon is whether one object is hotter or colder than another one, taller or shorter than another one, and so on and so forth. In other words, only those attributes that can be compared with an external reference are open to scientific scrutiny. This evidently restricts the domain of science. Another point worth insisting on is that a phenomenon can be said to be understood only when we have understood its intrinsic properties and its behavior in its usual context. For example, a respiratory disease is not spread by inoculation. However, following Koch's postulate, contagion is only verified via inoculation. Hence, the need to study them both in isolation and in their natural surroundings over time and space. As is the case with diseases, some effects and their range may not be immediately noticeable. Now, all this is very good, but what purpose do scientific theories actually serve? They provide us with unifying descriptions and explanations of disparate phenomena and enable us to predict. All three aspects are interrelated. The descriptive part tends to answer the question how, and the explanatory part tries to modestly answer the much more difficult question why. Both are often the same and closely connected. A purely predictive description based solely on empirical foundations, for example, simply stating that a thrown object will eventually fall without understanding why it falls, does not allow us to make sense of the phenomenon and therefore to master it. The quality of predictions depends on the quality of explanations, and conversely, the strength of explanations follows from their predictive scope. Otherwise, they run the risk of becoming fanciful. However, even if an explanation leads to some correct predictions, this does not mean that it is correct. Such was the case of Isaac Newton's corpuscular theory of light, later seen to be based on invalid assumptions. The search for explanations, however, forces us to use concepts, such as atoms, for example. We have no way of determining whether these are merely unobservable as a consequence of the limitations of our senses, or whether they are pure constructs of the human mind to account for mundane experience. They are also indefinable from within science. However, and this is fundamental, the scientific soundness of concepts must be confirmed by perceptible and describable effects, and they must be replaced by more appropriate ones if reasoned observation demands it. Their study would otherwise amount to metaphysics. In summary, science is the reasoned study based on reproducible and sufficiently reproduced observation. One of the properties of the sense-perceptible world that can be described by comparison, and two of the sense-perceptible effects attributed to the concepts thus induce. Thirdly, the study includes interactions with the natural environment. Hence, the difference between a scientific and a more mundane approach is one of degree rather than of kind. It brings precision and systematization where these lacked. For instance, we all have some idea of what fruits and vegetables are, and this serves us fine. The ordinary usage is founded on associations with instances we have come to consider as similar for vague reasons, often cultural ones. Fruit is usually eaten at dessert. However, the scientific definition of a fruit is that of an organ that contains seeds, which protects these as they develop and aids in their dispersal. Therefore, tomatoes and cucumbers are fruits, contrary to the widely held belief that they are vegetables. In other words, science makes precise the similarities and differences between comparable objects by taking observation beyond the superficial, thereby reducing ambiguities. As we saw, science rests on observation. If it disagrees with experiment, it is wrong. For Richard Feynman, in that statement is the key to science. Let me add that experiment is not merely observation. It also involves the observer's intervention. Science is also based on ideas. Observations and ideas are inextricably connected. On the one hand, observation keeps flights of fancies in check. Observation enables us to leave aside unsuitable ideas and prompts better ones. On the other hand, observing outside of a theoretical framework is impossible. Our senses are at every instant submerged by innumerable external data. Every phenomenon has multiple aspects, and it is beyond the capacity of the human mind to take them all into account. We have to make a choice. Hence, the necessity of rapidly intuiting what it is one wishes to observe and why. Observing at random is futile. Observation must therefore be preceded by an idea of what is likely to be useful. In other words, as remarked by Feynman, judgment about what to observe and what to pay attention to plays a vital role. There cannot be any systematic observation without preconceptions. Hence, ideas enter science from the very beginning. They guide observation and they give it meaning. Therefore, science is far from objective. Thanks to reproducible observation, our theories are as objective as possible, but they are highly subjective, not only because they are equally based on ideas, but for multiple other reasons, not least because we see the world through our perceptions. We cannot know what it actually is. To quote another physicist, Werner Heisenberg, man's argument cannot simply speak of nature in itself. Science always presupposes the existence of man. This is why questioning received ideas, taking nothing at face value, are characteristic of a scientific approach. Scientific thinkers of all eras and traditions have insisted on the importance of doubt. Theories should not necessarily be rejected, but their acceptance should not be passive. And if they are rejected, it must not be because of prejudice. In short, to quote chemist Dmitry Mendeleev, father of the periodic table of elements, science knows no final truth. Scientific theories are ever-changing. Scientific knowledge is constantly evolving. It is the exact opposite of dogma. Science is by definition the only approach to knowledge with inbuilt doubt about its own statements. In other words, an approach acknowledging that its theories are open to modification, even to complete repudiation, that they are ephemeral and in a constant process of revision, but of a revision that must itself conform with the data available. This is why, as remarked by Feynman, one should never say, "Science has shown," but "this experiment, this effect has shown." The statement "science has shown" suggests that its pronouncements are unalterable and absolute, which is incompatible with its nature. But what is science if it is in a constant flux? It is the messy, yet heroic human attempt to understand the workings of the universe by stubbornly going on in the face of insurmountable obstacles, in the face of elusive comprehension, of innumerable failures and errors, which in turn give rise to new questions requiring answers. It is the nearest we can get to certitudes, yet it is unable to offer any certitudes because certitudes are incompatible with our human condition.